So we are still talking about the first law of thermodynamics. And heat transactions. Is that where we're at? Yeah, section 2.4, heat transactions. Okay. Kelly, what was U, big U again? What was that? What did they call that? The what energy? It was the internal energy. Now let's back up a little bit. Heat was what symbol?
Q.
Q. Enthalpy will be what symbol? We haven't talked about it yet. Big H. Yeah. Okay, so internal energy is capital U, but what did it represent, Jeff? What it's supposed to represent what?
The capital U?
Yeah. I mean, there's all these energies, but
The energy, total energy in the system?
total energy, it doesn't matter what the mode, what the, everything. Any type of energy you can think of, it takes it all into account. That's the internal energy. Okay. So how about W, Kevin?
Work.
Work. Okay. Now, I don't know if you've got to look ahead or you can kind of gather from what we've talked about so far. The only type of work we're going to have problems with involve what in this class? Work where a gas is, yeah, it's pushing against the surroundings, right? It's doing work on the surroundings. Or the surroundings could be doing what to the compressing. So the surroundings is doing work on the system. So that's the only type of work we're going to be talking about. Well, if that's the case, Gloriana, what the heck is that dW with a little e?
Where?
All right. The very first top expression, right? At the very top.
Oh. Isn't that distance?
What's a little d mean? Look at the little d's in front of all of these. Infinitesimal. You're doing a dinky, minute, extremely small amount of change, right? Instead of having a delta, so I maybe think of this way. That we always thought of that as change, right? Final minus initial. Macroscopic. So the little d would be microscopic. Now that's two ways to look at it. We also use the terms reversible and irreversible changes or processes. Which is which there? The delta or little d for pick one. Reversible. Reversible is the little d. Because things are supposed to be happening so slowly that you're at equilibrium every step of the way. So you can go backwards. Go backwards in time. But there is no time. But you can go backwards in the process. Time isn't a factor. So irreversible would be, boom, it's done. The big delta, or what we're thinking of as macroscopic. So what we're getting at is asking Gloriana, what's this little DWE doing there? We don't really care. It's all the types of work that we're not going to talk about. Remember there's a table, electrical work, and all these guys? The only type of work, this is the only one worry about, right? That's the only one that concerns us, is the expansion or compression, okay? And whether it's done reversibly, or in this case, it's done irreversibly, right? If you have P delta V. Where are we? Here we are. Okay, so this is really our expression, right? U equals Q plus W. Okay, so what they want to get into is, let's do these changes. Let's see how the internal energy changes, whether we keep volume constant, pressure constant, that sort of thing. But take a look at this guy. If you're going to keep volume constant, Okay, you're going to do a little reaction, right? Look at how this thing is built. Talk about, it weighs like 20 pounds in the first place. Look at all the threads. And we haven't even got to the inner chamber yet. So there's a little combustion reaction is going to happen in here. So you set all this stuff up. The reaction happens, right? We're talking about gases and things, but the volume can't change. This is essentially a what when that reaction happens and all that pressure builds up? Just the opposite. A bomb, right? Because all these gases are created. And they can't expand because it's a constant volume. So they call this a what calorimeter? Bomb calorimeter. And so there's really not a whole lot to that lab, though. I mean, you perform the reaction, you measure a small temperature change, one of a substance that's known so you can calibrate the instrument, and the other one is your unknowns. But the point is that we had U equals Q plus W. Now all of a sudden they're saying bomb calorimeter, and now they're saying delta U is Q with a little subscript V. But Kevin, where's the W? Right? We just said U is Q plus W. Now they're changing it on us. Where's the W? W has to be what? Has to be 0. Why?
It's not doing any work on the surroundings
Why?
because it's inside the calorimeter.
And the calorimeter can't change its volume. All right, you can't do any. Remember, what's the only type of work we're talking about? PV work, or you can call it PV work, or you can call it compression work or expansion work, that type of work, right? So if you're in a bomb calorimeter, your delta U is just your Q. And the little V subscript is trying to give you a hint, right? It's trying to say, Kelly, what? What's that little V subscript doing on the Q? They're trying to tell you, hey, this is special conditions here. This isn't always true. This is only when what is constant. What's not changing in that bomb calorimeter? The volume, right? The volume can't change. Something smells like it's burning, doesn't it? You guys were smoking. No, it smells like matches or something.
Maybe something.
Yeah, something, right? Jeez. Kind of smells good, though. So they're trying to say this is a special case, right? This always holds true. Always holds true. This, no. Only under special conditions. Volume has to be held constant. Not always true. Okay? So here's another definition. That always holds true. If you know the delta T, now you can get Q out of this expression. Delta T is probably what, Eric? Change in temperature. Okay. That looks like a macroscopic or a microscopic change to you, Gloriana, that change in temperature.
Macro.
Macro, right? And just read the final temperature or the initial temperature on the thermometer, you're done. Okay? So you take that change in temperature times big C. Big C is the calorimeter constant. So what must be its units?
1 over Kelvin. Or no, wait,
Joules
joules.
over Kelvin. Or they could have joules over Celsius or something, right? Because you want whatever units your temperature in, they have to cancel. So what they're saying for a calorimeter constant, a lot of times it's just joules per degree Celsius. And it's just how much energy does it take, right? how much energy does it take to raise that this hunk of metal 1 degree Celsius? How much energy does it take to raise it 1 degree Celsius? That is the calorimeter constant. So, and then you can get your Q out of that. You measure the change in temperature and you get the heat generated.
Qs and joules.
What's that?
Qs and joules.
Yeah, that's the only unit we're going to use for energy, is joules. Otherwise, life would be so complicated, that metric system. Okay, so you can get your Q this way, or get it this way. Now, this was concept preview time, Melissa. What was IVT? IV and T.
You said Melissa, right?
Yeah. Wow, I said Melissa. Well, your teammate Alyssa can help you. IV and T, what were those? Eric knows. You don't?
I don't know what I is.
I is?
Thinking of a current.
Current.
It's current?
Okay.
Thinking of a current.
V is?
Current. Volume?
Volts.
Oh,
Little t is?
Time.
Time. Now don't see the curvy nature of this, don't let that confuse you. I'm just copying what the book has, right? So current, voltage, and time. Okay. So just some expressions for the what calorimeter? Bomb calorimeter. Right. Okay, and there'll probably be some homework on that. But they introduce it because they want to talk about these heat capacities. So, you go to Pizza Patron, it's fresh out of the oven, right? You take a bite out of it, and it just burns. Because what has a very high heat capacity?
Carbohydrate?
And that pizza, what has a very high heat capacity? You have to blow on it forever for it to cool down. I think it's the tomato sauce. I think it's the tomato paste, because that cheese turns hard pretty quick. But that tomato paste, that stuff has a very high heat capacity. It's worse than water. So it takes forever for it to cool down. So heat capacity, the amount of energy it takes to raise something 1 degree Celsius. Sounds very much like the calorimeter constant. It is. Right. Except calorimeter constant is kind of nice because the term is different, because this is a calorimeter. It's a hunk of equipment. So you could calculate its heat capacity, but calorimeter constant just sounds better, more jargon. But they're the exact same things. Okay, so these heat capacities, you could notice how they have the symbol big C for heat capacity. The little v probably means what still? Shelby, what's the little v mean? The little v subscript, just like it did up here.
Oh, volt?
No. Kelly, what did it mean? It meant what's constant? Volume. Volume was constant. So the heat capacity at constant volume. Okay. What's the little m? Because not only did they didn't stop there, they didn't just write CV. They wrote CVM in this case. What's the m? Molar, right? So it's just find your heat capacity at constant volume, divide it by the number of moles, and you'll have CVM. So they're just playing around with our units. Anyway, you plot how the internal energy changes with respect to temperature. Here it is right here. How the internal energy changes with respect to temperature. How does it change? Okay. That slope would be your heat capacity at constant volume. Okay. Does it look like it changes with temperature according to that plot? Yeah, most definitely, right? But I'm kind of stuck with it. So a lot of times we just assume it's going to be constant, but we'll see. Not always. It'll come down. Okay. Do you see how they jumped from here over to there? What they did is they brought this part up here, right? So they had CVDT, du, right? And then they can integrate. So they're just playing around with this stuff. And how that if you multiply heat capacity times change in temperature, right, the temperature units cancel, multiply it by change in temp, and you get energy, QV. So they're just playing around with this stuff a little bit. So, but in lab, I guess you can keep volume constant. But if it's working on the bench, Shelby, what's really constant? Just working on the lab bench, do an experiment. What's constant? The pressure. Much more practical. That's why you see enthalpy a lot more often than molar heat capacity at constant volume. You have to use a bomb calorimeter for that one. Enthalpy. Okay. I don't want to be skipping anything. What am I? Have I skipped anything?
No, you're following nicely.
Am I?
Yeah.
Okay. Oh, yeah, I'm looking at the wrong part. Okay. So now we're at enthalpy. Yeah, we talked about all that. Haven't missed anything. Okay. So we're allowed to change what now? We can change volume. Now we can do work. Now our little work expressions are gonna be messing things up a little bit. Okay. What if it was isothermal? Whatever, pick the change. I mean, you have a compression, expansion, whatever. Isothermal process. They can make it as complicated and ugly as they want, but the term isothermal is in there. The change in U is going to be 0, right? Remember that, because the only way to change, we're talking about what type of gas first? Ideal gas, right? All this is about an ideal gas. Otherwise, life is way too complicated and ugly. So we're talking about an ideal gas. The only way to change the internal energy of an ideal gas is to change its temperature. Make it go faster or slower, right? Okay. What about for enthalpy? Right? So we're saying it's an isothermal process. What happens to delta H? Because right away we can say delta U is 0, right? Now we're done. But what about delta H? So let's put a little delta in front of everything. So we're talking about changes. So the change in enthalpy is equal to the change in internal energy plus the change in, well, P and V. We're interested in temperature, though. So PV is really equal to what? nRT. Okay. So we're just looking at changes here. So just change in enthalpy is the change in internal energy plus the change in nRT. In these problems that you've worked so far in your chemical career here, do we ever really change the amount of gas? It's a sealed container. You've got a system. They're not going to change the number of moles of gas. They're not going to add some gas. That's what they have is what they have. So that won't change. Will R change? No, it's a gas constant. So what you end up with is delta U. Oh, sorry. If it's isothermal, delta U is 0. Yeah, so 0 plus, you can pull the N and R out, you get delta T. But it's isothermal, so delta T is 0. So we not only if it's isothermal for an ideal gas, which is pretty much all of our problems, right away you can scribble down change in internal energy 0. You can also write change in. Yeah, you can write delta T as 0, but delta H is 0. Just things that you scribble down right away. Doesn't matter how complicated they make the process. So just remember that for the homework. Okay, that'll make your life a lot easier. So your Q, heat exchanged at constant pressure, is how enthalpy is defined. They're the same. Okay. capacity at, oh, we're talking about heat capacity at constant pressure, so I was just sticking with it. So you plot enthalpy versus temperature. That's what they did. Plot enthalpy versus temperature. And does it look like and the slope would be our heat capacity. Divided by the number of moles, you'd have molar heat capacity. But does it look like that slope is changing as the temperature changes? Yeah, it does. And here's an expression. They didn't do this for volume, heat capacity at constant volume, but they do for heat capacity at constant pressure. And then they give us the little fudge factors for different gases so you can get the right answers because it changes, right? Temperature did, volume did too. And here's the table where you get these guys from. Okay. So what they're getting at here is, let's see, if you, I gotta clean this up a little bit. If I bring the dt over there, can I make space? I can make space. Let's see if you recognize this. Okay. I bring the Cp, I've got the dt, and I've got the delta H over there. So then we do our little integration thing here, right? We'll get our, see what I did? All I did is I just rearranged this. I brought the dt over. I hope I don't lose you, right? And then we integrate both sides to get rid of little differentials. Do it in the infinitesimal steps. It's an integral, right? We'll get delta H. And you can pull stuff out of the integral if it doesn't change with temperature. But you just said, oh, it changes with temperature, so don't pull it out of the integral. So you have to integrate it. So what's the equation that you put in there for it? Here it is. You put that right in here. And then you integrate. Do you remember doing that? Please say yes. When did we do that? Yeah, the concept review. Okay, you already did this. Okay. No. There was no life before this class. So yeah, so we did that already. So we have an expression. Just check out the concept review. Okay. So that's how you can get an expression for the change in enthalpy. If they give you a little A's and B's. See how this is really hard to see, but let me blow one up. 4.77, and the table says B divided by 10 to the negative 3 Kelvin. Okay, that's just part of that table. So your B, if you read this table right, you're going to say B is equal to what? Just to get used to reading these tables.
For reversal?
Yeah, I'm just reading this top one. So B isn't just 4.77. It's 4.77. Is it divided or times? Times, right? Remember, that's his convention. He has his variable, slash, and then the units. But not only does he have units this time, he also has a number. So you have to put your 4.77 and then whatever is down there. Not just the unit that we usually do, but he has a 10 to the negative 3 also. Okay? So it's just something to get used to. I think that's about it. Okay, let's try some of these. Okay, a sample consisting of 1 mole of argon is expanded isothermally at 0 degrees Celsius from 22.4 to 44.8 liters. First it's done reversibly and then against a constant external pressure equal to the final pressure of the gas. and C again freely. Man, there's 3 cases here. For all the 3, we have to find this. All right? So we've got 1 mole of argon. I'm just trying to list some of this stuff out here. Isothermal expansion. All right. At 0 degrees Celsius. 22.4 to 44.8 liters. Sometimes it helps me when I list this stuff out, but anyway. So let's find Q, W, delta U, delta H. A is reversibly. Okay. So we need a Q, a W, a delta U, and a delta H if we do this reversibly. Mole of argon, expand it, let it expand isothermally, right?
Reversibly with all the D expressions.
Reversibly. Now there's some easy answers right off the bat though. Which ones do you know right away?
DW is
We know delta U is 0. Delta U is OJ. And delta H is 0. Okay. We still need Q's and W's. Now, good habit would be, unless you've got a really good memory, I'd be looking at that equation sheet or looking at the notes, but it could have been something discussed last time. Hopefully I have it. Do I have an equation sheet?
Yeah.
What page is it on?
25.
Thank you. Yeah, page 25. Okay, we do have an equation sheet. Nice. Okay. So Kevin, any idea what to do here? We need a Q and a W. Shelby, got an idea?
Negative external pressure and the change in volume will work.
No, the negative nRT. That way.
Delta U equals Q plus W, and at 0 then have to be 0.
It's the
Okay, there's a lot of ideas coming out here. One was delta U equals Q plus W. Definition always works no matter how complicated life is. But we know delta U is 0. So that means Q equals negative W. Okay. So we'll need this. That means all we got to do is find one of them and put a minus sign on there, right? Okay, so we'll need that. And someone was saying something else, and I forgot what it was. You said W is...
Negative external pressure and the change in volume.
Okay. But that's for what type of work? If the work was done macroscopically, we just let it happen. The word for that would be not reversible, but irreversible. So remember that for the, what is that, part? Another part, when you're doing irreversibly. All right, so not that one. So the equation for reversible work was negative nRT. There it is.
You said that was for macroscopic?
Because there's a triangle in it.
Oh, okay.
All right, so that was for a irreversible. Do we know everything in this expression to get W? How about the, remember I was harping on units? Their volume is in liters. Do we have to get all the way to cubic meters? Because that's a standard metric unit for volume. They'll cancel. Exactly, so why mess with it? You can, if you want to go through all the work of converting to cubic meters. Do you hear what Melissa's saying? They'll cancel. Negative 1. Yes, liters over liters. Right, they'll cancel. What R do we use? 3.314 joules per Kelvin mole. T 273. Natural log. V final over V initial. That'll be what over what? 44. Yeah, 44.8, 22.4. See, the liters cancel.
Will that always happen?
In that expression, yeah. Right? In that expression. So we can get our work. Multiply it by a -1, you'll have the Q. And we'll have found everything for part A. I don't know.
Negative 4,000.
I got 15, negative 1,500. Right around there. Oh, I forgot to LN. Just kidding, guys. Okay.
So what do you guys get? Negative 1,500 or something?
Negative 1570.
Negative 1,570 something. In joules. There's my W. So that means Q must be positive 1,570 joules. Okay, that's all. That's just for part A. Part B now. Oh, let's do red. Part B was against a constant external pressure equal to the final pressure of the gas. So expansion against PF, right? That's how I would write final pressure. Are there any easy ones, Gloriana? Are there any easy answers?
No.
You know that W is 0, right? Oh, no.
No easy ones? Read it careful, right? The part A, B, and C starts after this. All of this is true for all three parts.
And delta U and delta
What
H
word is it?
Still 0.
Delta U and delta H are still 0 because it's
Isothermal.
isothermal. Right? You see that, Gloriana? Right? Because this whole, that
Oh, I
isothermal
see.
expansion, they give you the temperature and the at which the isothermal expansion occurs. They give you the change in volume. And then there's three ways to do it, that expansion. But they're all isothermal. Good. So that means delta U is 0. Delta H is 0. Okay. So we need the remaining two. Kevin, you're mumbling about something.
What?
You're mumbling about something. What were you saying?
The external pressure.
Yeah.
Equation. Negative P external pressure change in volume.
Good.
Where do you know
From last time.
Is that on our cheat sheet?
Yeah.
Yeah, just written up on top. So you have to recognize the parameters, right? If you see an expression, not only do you have to know what the name of the variables are, but when you can use that expression. Okay? So this W is minus P external delta V. Yeah, it's a work, but you can't always use it. It has to be a irreversible process, right? It's just let it go. Okay? And what can't change? when you use that expression?
Pressure.
Pressure can't change. It's work that's happening really quickly, and that pressure has to be constant. You're pushing against a constant pressure. Okay.
Without the units of volume, we have degree of speed.
Oh, good idea. I would definitely agree with that. This had better be in cubic meters. How about that pressure?
Pascal.
Had better be in pascals. Okay, so that's your starting point. How do you get, well, to get the change in volume, we'll just subtract the two, convert it into cubic meters. How do you convert liters into cubic meters again?
1 liter is the cubic decimeter.
Yeah, you can go that route. Or 1 liter is 1,000 cubic centimeters, and then go to meters that way. Right, that's concept preview again. How about, so that's this part. Does that make sense? You guys follow that?
So what's the external pressure?
Yeah, there you go. How about the external pressure?
Probably just go sea level or whatever.
We can convert to,
Why do we know it's 1 ATM?
yeah, how do you know it's 1 ATM?
Isn't it always 1 ATM?
Pressure at sea level or whatever.
External pressure is always 1 ATM.
If they would have said STP. But they said against a constant external pressure equal to the final pressure of the gas. Well, what the, how are you going to find that out?
PV equals nRT.
Ooh. Will that help?
Unit volume and unit temperature.
At what? One thing be really what I'm really comfortable with, because I've done it so much, put subscripts on the ideal gas law. You can put subscripts on a lot of equations, but be consistent with it. And some things make sense to put subscripts on, others don't. Like if I want PF, fine. Does it make sense to put an F on the V? Was that volume changing?
Yes.
Yeah, so it makes sense to put an F on the V. Does it make sense to put an F on the N? No, so it's kind of helpful conceptually to me if I don't then. How about on the R? On the T?
No, it was isothermal.
It's isothermal. So PF, VF equals nRT. And just solve for PF. And then, like Kevin said, get it into pascals. I think it'd be easiest to get this guy in atmospheres, because volume's already in liters, but it's up to you. So you could use that R, that's 0.0821 liter atmosphere per mole Kelvin. And it might be a little less converting to do, but either way, it doesn't matter. Just make sure that pressure's in pascals.
Yeah, I got 1 ATM. Yeah.
Really? You got 1 ATM?
Yeah, 1.0008.
I read that somewhere. I thought it was 1.
No, it's not. Oh! It's,
1.0821.
what's the reason why it's 1 here? What's the magic? If you take the temperature 0 degrees Celsius, ideal gas, the temperature 0 degrees Celsius, you take exactly 22.414 liters of that gas. The pressure is going to be what? 1 ATM. That's the magic number with 22.414 liters of any gas in the ideal gas law. So don't expect it to be 1 every time. It should really be 1 point. It shouldn't exactly be 1 because the change in volume wasn't exactly 22.414.
I got 1.000000.
Yeah, it shouldn't be exactly 1, but it should be close.
Because if it's final V, it's
So
25.
the work was 22
Yeah.
joules, right?
Are we using delta V or final V?
The work
You're
was
using
24
V final
joules,
minus V
22
initial,
joules.
because that's what the expression's saying.
Did you do the?
But you take 44.8 minus 22.4, you get 22.4.
Did you already convert the?
Oh, yeah,
Okay,
it's
so
once you put
PV
in the
doesn't
equation,
actually
it has to be
exceed delta
Pascals.
V. And the
So
volume is
here I would plug
So
in
it's what?
your final volume, right? Your final volume
Take
is,
1 times whatever the Pascal is.
your final volume is
Which is
44.8.
101.
44.8 has to be going in here.
It's
Okay, when you
22.4.
put in 44.8, you have
times
to say
6 is
1.
fit, right? It's like 1.
So for me,
Yeah, you're not going to get 1 here, Kevin.
where?
The final volume is 44.8.
Because you did change in volume. You
Oh,
have to do
I
the
did.
final volume.
Yeah.
It's 0.5.
Now we're confusing.
Oh, yeah.
Yeah.
0.5?
Divide all
Oh, I
The
did.
wrong volume is used.
Yeah, it's VF. So VF is 44.8. Right? Because we're after PF. You're right, the delta V would be 22.4 liters.
What? 550?
51.63. Oh, I forgot the 8.
So what'd you get for your work?
Oh, no, I haven't done that part yet.
Okay.
What'd you guys get for the volume?
A liter equals 1 decimeter
Cubed. Or a liter's 1,000 cubic centimeters. You can go either route. So your PF, you guys are getting like half an atmosphere.
So I got 7 joules. What?
This making sense, Kelly? Where'd we lose you?
I was gonna ask about the other one. How come we pay
2.24 times 10 to the negative
this on instead of the other on?
Okay, you pick the one that's the most convenient, and in the equation we're putting it into is right here, right? So, in work, it should be joules, because that's energy. So if you want joules, it's so much more convenient to pick this one. Otherwise, you're going to have to do converting. You're going to end up in some metric or some English unit for power.
Okay.
So definitely use this one.
Oh, no, it's gonna cancel out.
And those cancel out, so you don't care.
So it's negative 11.34.
It's negative what?
1134.8.
Yeah.
And then so then that's what, so Q is the opposite
So
of that.
22.4 times
So you negative 1134 joules.
Yeah.
Did you guys get negative 1134 joules?
2.24 times 10 to the negative 2 for the volume, right?
Okay.
Right, yeah, that's right. Okay.
Is that the answer, Dr. Smith?
I don't know. I'm just, you guys all got it. Has to be right. Right? So then you have 1134 joules. And then Q has to be the opposite of that.
Right.
Positive.
What? Negative 11.34, 48 joules.
I know it was negative 1135.
That's close enough. Just rounding.
So then would freely be the opposite? I guess 0. So
Wait, I didn't put that.
So
Not like a number bigger.
check what you got for your pascals and your cubic meters. Check with Eric. What did he get for his pascals?
Did you get
Pascals
this?
were. What'd you put in? 2. that 2.24 times 10 to the negative 2?
Yeah.
And yeah, that should be the pascals. Oh, you did
No.
22.4, 2.24.
Why 2.2?
Because it was 0.0224, so that's 2.24
Point
times 10 to the
oh
negative
two two four.
2. Yeah, it's 2.24 times.
You're converting your liters to cubic meters wrong.
Okay.
That's the part.
Okay, so
That's the
you
part
take
you're doing wrong.
22.4 times what?
10 to the negative 2. 2.24 times 10 to the negative 2.
So if you got B, see if you can figure out the answers to C.
Oh, 2 point. Well, why 2.24?
It's this conversion right here. 22 point, you do the change in volume, so that equals 22.4 liters. 1 liter is the same as a cubic deciliter.
How do you know that's
Oh,
a
is void
decimal?
zero and there's no
You just
external
know
pressure?
Okay. Okay.
And
No, but how do you know this?
So everything's
This is a decimal.
because of
Is
liter
everything
is
zero
equal
because
to
there's no
Oh,
external
I
pressure?
see.
It's like
Oh, I'm screwed up.
It's
Okay.
like a
Is everything 0 for part C?
I was wondering that.
Yeah. Is it supposed to be?
Why is it supposed to be? Why is everything supposed to be?
External pressure, the external pressure is 0, and you multiply that by volume.
Yeah. So if the W is 0, the Q's got to be 0. And delta U and delta H are so. So everything is 0.
Because deci is like 10 liters. So,
But you scored this, right?
yeah. So it's like divided by 1,000.
That made sense?
So it's the 0.0224 and moves the 22.4 3 places.
See, we have a couple minutes. See if you can at least get started on number 2.5 here. Oh. I don't think we talked about that. They said monatomic perfect gas for a reason. I don't think we...
It's that PIVI equals PFVI? Or no?
Oh, why? That's... Oh, I screwed up in that. Look at page 21 of the notes. Shoot, how did that get there?
We're just supposed to do 2.6?
I think that this homework question isn't supposed to be where it is.
Should we just save it for next time?
Which one?
We could.
2.5?
We could. Let's move 2.5 to...
Yeah, we can replace 2.8.
2.8 has to do what you guys did.
Yeah. Let's... Okay, on page 22 of your class outline, cross out 2.8 and write 2.5. And then for the assignment for today, cross out 2.5 and write 2.8. Right, 'cause 2.8. Yeah. Do that. So on page 20, cross out 2.5 and write 2.8. And on page 22, cross out 2.8 and write 2.5. Then don't have to worry about this monatomic perfect gas thing. Okay, so we are doing 2. We're out of time. But give these problems a shot. I'll be glad to help you out on any of them.